السلام عليكم ورحمة الله وبركاته. مرحبا بكم جميعا في هذا السيمينار المخصص لشرح الفصل العاشر من كتاب Introduction to Robotics للعالم جون تيرج. اليوم حديثنا بموضوع يعتبر من ركائز التحكم الحديث، وهو التحكم الغير الخطي أو النيرميليا كنترول. في البداية خلينا نسأل نفسنا سؤال جوهري: هل الأنظمة الروبوتية دي أنظمة خطية ولا لا؟ قبل ما نمشي المعادلات الرياضية، في الواقع هي الأنظمة الروبوتية ما خطية بطبيعتها. معظمها بتتعامل في الحياة العملية والبيئات الصناعية بطريقة غير خطية بالكامل. النماذج اللي درسناها في الأبواب السابقة هي كانت تقريب لنقطة معينة أو شرح لنقطة معينة من الواقع حق الروبوت، لكن لما يبتعد الروبوت عن النقطة دي فإما السرعة بتزيد أو بيحمل حمل ثقيل أو بيعمل في بيئة متغيرة، بتبدأ الأنظمة الخطية تفقد دقتها، الأكيوريسي حقتها بتقل، وهنا بفشل المتحكم الخطي التقليدي يحقق لها الأداء المطلوب. عشان كده هي الأنظمة الخطية ما بتقدر تعمل لها كنترول للأنظمة الروبوتية. إذا لماذا إحنا درسنا الأنظمة الخطية؟ أول شيء بيمنحنا أساس قوي من معادلات رياضية زي تحويل لابلاس ترانسفورم والترانسفير فانكشن. الأدوات دي نحن مباشرة ما بنقدر نطبقها على الأنظمة الخطية مع الأسف، لكن بنقدر نلغي الخطية، ودي بتناوله لقدام في نفس الفصل ده. طيب، لماذا التحكم غير الخطي؟ الروبوت في الواقع العملي تحتوي على احتكاك وجاذبية وقيود فيزيائية تجعلها غير خطية بالضرورة. طيب، نيجي للفرق بين الأنظمة الخطية والغير خطية. معروف إنه نحن درسنا في اللينير سيستم إنه المعادلة الديناميكية حقتها x دوت بتساوي x زائد البي يو، والواي بتساوي سي اكس زائد الدي يو. الخصائص حقت المعادلة دي بتحقق لنا معادلة أو الخاصية حقت السوبر بوزيشن، والسلوك بيكون منتظم قابل للتنبؤ، والمعاملات بتكون ثابتة. بينما في الأنظمة الروبوتية الإكس دوت بيساوي اف اوف يو اكس تي، والاتش والواي بيساوي اتش اوف اكس يو تي، حيث إن الاف والاتش دوال غير خطية. دي ما بتحقق لي خاصية التراكم، وتحتوي على سلوكيات معقدة جدا. برضو بيحتوي لي على قوة كيرلس والقوة الطاردة المركزية اللي هي بتتغير لحظيا مع تغير البوزيشن والفلوسيتي. برضو الجرافيتي تورك بتعتمد بشكل مباشر على الساين والكوساين. الحدود الميكانيكية والفيزيائية للمحركات برضو شوية ساتوريشن. كل العوامل دي بتخلي لي نظام غير الخطي بطبيعته. لذلك فإن فهم النظام غير الخطي هي ضرورة حتمية لأي روبوتكس انجينير يسعى إنه يصمم لي نظام تحكم يعمل بموثوقية في ظروف التشغيل العادية. نجي لأمثلة. طيب، هنا عندي أمثلة برضو. النظام الأصلي بيكون f of ux ساي x دوت، هو نظام غير خطي. بيكون عندنا قانون تحكم بنختار اليو عشان نلغي النون لينير ونحوله لنظام مغلق، نظام خطي مغلق، حيث إنه بيساوي لي الكي بي في الايرور زائد الاي دوت اوف دي في اي دوت في الكي دي زائد اي دبل دوت. فده بيكون نظام مغلق خطي. نيجي المثال حقنا اللي هو زراعة روبوتية لمفصل واحد. المعادلة دي هي اللي بتتحكم لي في حركة المفصل واحد أو الون جوينت، حيث المعادلة بتقول لي جي في سيتا دبل دوت زائد البي سيتا دوت زائد الجي في سيتا يساوي لي التورك، حيث إنه السيتا هي زاوية المفصل المراد التحكم به، وجي هي هي العزم المفصل أو عزم الوصول الذاتي، والبي معامل الاحتكاك واللزوجية. طيب نيجي لمعادلة تانية. أو نفس المعادلة دي لما نيجي نطبقها على روبوت متعدد المفاصل، هي المعادلة ما فيها حاجة. لو داير أطبق مثلا إذا ادوني في مسألة ما إنه عزم الوصول الذاتي هو مثلا 0.5 كيلو جرام في المتر المربع، والبي 0.1 نيوتن في المتر، مضروبة في الاس على الراديان، والجاذبية اللي هي الام دي ال بتساوي 5 نيوتن في المتر. الزاوية حقتي كانت مثلا واي على 4 راديان. نعوض الأرقام دي بس اللي هي بتكون 0.5 في سيتا زائد 0.1 في سيتا زائد 5 ساين سيتا بيساوي التورك. بعد ما عوضنا وجبنا التورك بيساوي لي شنو؟ بيساوي لي 5 في ساين سيتا زائد 0.5 سيتا دي ناقص كي دي، سيتا ناقص سيتا دي ناقص الكي دي، سيتا ناقص سيتا دي. وبعدها بنعرف الايرور اللي هي سيتا ناقص سيتا دي، ونعوض المعادلة الديناميكية. طيب هنا لو داير أطبق لروبوت متعدد المفاصل، النظام العام بيقول لي ام كيو دبل دوت زائد السي في الكيو دوت مضروبة للكيو دوت زائد الدي كيو زائد التي. القانون ده برضه بيقول لي فوق الام دوت كيو دي طيب زي ما شايفين يعني في القانون النموذج ده بحول لي كامل تحويل كامل لنظام خطي يستخدم تقنيات التحكم الخطي المشهورة وتكون الأداء جيد. العيوب تتطلب معرفة ولا قاعد يسجل فيديو للجامعة، قاعد يتكلم ولذلك ناس الجامعة شافوه قال لي ده وجه الجاك ده، قلت له ما كابوس ده وجه.
السلام عليكم ورحمة الله. الدراسة حتكون عن التحكم في اللاخطية للأنظمة، أنظمة الروبوتات. High perform control of robotic manipulators through torque regulation is a difficult task. The difficulty arises from the complexity of the dynamic model of the arm. We can specify this to regulate torque that develops nonlinear behavior of the arm's dynamic. Equal the equation of the motion of robotic arm. This is the inertial term have the inertia matrix, and this component have the Coriolis forces and centrifugal force, and the gravitational terms plus dissipative power that in friction, and the torque developed, and this represents the control input in our model. For an n-axis robot, the manipulator is modeled as a simultaneous system of n highly coupled nonlinear second-order differential equations. So, what's the reason for nonlinearity? One of the most complex terms in the dynamic model is the velocity coupling terms, which generated by the centrifugal and Coriolis forces. since the k component of the velocity coupling vector is of the form is like this. Consequently, for each point q in joint space, the velocity component is 10 to 0 as and if the norm of the speed for that joint is 10 to 0. Therefore, if the speed of the robotic arm is reduced sufficiently, the dynamic model simplifies in the sense that the effect of centrifugal and Coriolis forces can become small in comparison with the terms that do not depend on the q dot. So if the robot is operated in a single axis mode where the joints are activated one at a time rather than simultaneously, then velocity coupling due to Coriolis force but not centrifugal force the Coriolis force is dissipated completely independent of the arm speed. For frictional term, this is the question for the friction term. The first term is the viscous friction and have a coefficient of pkv for the joint k, and the second term represents the dynamic friction where have coefficient of pkd for that joint. The third term represents the static or column friction and have its coefficient. Epsilon is a small positive parameter. From this equation, it's observable that as Vk tend to 0, the friction forces tend to be positive of the static form Bks in positive and minus. So we can interpret it as the torque or motion of joint K is initiated. It is clear that viscous friction is a linear function of Q dot in the joint K from this friction. That is the slope at that point. Whereas dynamic and static friction are discontinuous nonlinear function from this side of growing and growing down. For a well-designed robotic arm, particularly direct driven arm, the coefficient of friction will be small. The equation is only a rough model of the friction forces. A more comprehensive representation of friction may employ a term of this form, which depends on the position and velocity. The torque due to friction cannot be made arbitrarily small by operating the arm has a jump at reduced speed. This is because the term bq dot friction due to the velocity of that joint has a jump discontinuity at q dot equals 0. Indeed, it is clear from the picture that is relative that the relative effect of static friction become more pronounced as the arm speed is reduced. The third reason is that trigonometric term can also inherit non-linearity to rigid body, such as an inverted pendulum has the cosine term. Can be linear when theta tends to 0. ممكن نلخص نهاية الموضوع كله في التوصل بتاع اللاخطية في الدورانات الكبيرة، زائد الاقترانات اللي بتكون حاصلة بالتحويلات للسرعة ولمواضع العقدة. كما زيادة رتبة الروبوت بتؤدي إلى هذا التعقيد اللي بيحصل في هذه المتغيرات. The approach to controlling a robotic arm is to instead regulate the joint torque that built directly on the dynamic model. The approach is start from building state space formulation of the dynamic model of our robotic manipulator, then the research of solution, the simplest solution to the robot state equation, the constant solution of point of equilibrium are then investigated using the advanced stability technique based on Lyapunov method. These techniques are used to analyze single-axis PID control, a design method that is widely used in current chemical robots. Also there is more non-linear methods that are examined, including PD control with gravity compensation, computed torque control, variable structure control, and impedance control that aim at controlling position and forces by adjusting the mechanical impedance of the end effector to external forces generated by contact with manipulator environment. The state equation. Describe the dynamics model for the arm. It's helpful because it converts the 2n order of the system, second order system to first order system of 2n equation is to calculate control of the arm. Also we can dive the task into subtasks. Also it's helpful when we can take the system as black box and describe it by the state model and use the intelligent method such as fuzzy control or neural network in the black box model for the system, and another part is to controlling it by any method to be hybrid control. The key to transforming to state space form is the isolation of the acceleration vector of the joint. The state space model, including both a dynamic state equation and a kinematic output equation, as follow. We can define proposition. Define x, the state vector, equal q and velocity, position and velocity. Defining the velocity as q dot. So when we take inverse and derivative the q, we can see that v dot equal the inverse for initial. Then the velocity is a component of the inverse of inertia matrix product of those, where y equal wq, w of q, the tool configuration function from the tool configuration function that depends on the first n component of x, because it represents the tool tips, position and tool orientation. Such state is a function of t that include into the real set of 2n dimension. Summarizing it, a robotic arm with n axis can be modeled by first order nonlinear system of dimension 2n. This system has n inputs consist of the torque or forces delivered by the actuators and 6 outputs which specify the configuration of the tool. The block diagram of the modeling for the robotic arm in state space is like that. The solution method. Now we will introduce to the solution method. This study attention to nonlinear system of the following form: x dot equal gx of u. ut is the vector that is torque that developed by the motor actuator to the plant of the robots. If n is column vector of dimension n, we have the following initial condition of the initial state, that is m column vector. We will consider the system as an autonomous system to be easy simply for solution, such that u is constant, say equal r, so the model become more simple. For each t is larger than or equal to 0, some of r include to this space of n. There is an equilibrium point that include to Rm is an equilibrium of the system associated with the condition ut equal constant R, even only if this term equals 0. So it's a this is a constant solution for this equation. It's interest point that we will operate the system at. These are fundamental concepts that are applicable to nonlinear system in general. First method is the constant solutions. If the initial state equal the equilibrium point, the x developed in t as a function of t equal this point for each t greater than or equal 0. As mentioned previously above, the equilibrium points are the points of interest for our operation the joint, and it's a constant solution for the nonlinear system. We take this proposition: the torque have a constant value that is equivalent to the control law for some space Rn. Then the equilibrium point is even only if yields for gravitational term for the joint that operates in the state equilibrium state have a constant value, and the velocity of the equilibrium state equals 0. This lead to the robotic arm is motionless at the points of equilibrium depend on the value of the torque. The joint position constrained by this proposition can have a Venn solution, unique solution, or multiply solution. Next, we define the symmetric stability. An equilibrium point of the system of the nonlinear system is asymptotically stable even only if for each epsilon grade a positive integer, small positive integer, the existence for small delta, positive small delta, such that the measure for the initial condition to the equilibrium state is less than delta from the real analysis. Then this magnitude of the norm is less than the epsilon for each t greater than or equal to 0, and xt approach to x hat as t tend to infinity. Thus, if an equilibrium point is asymptotically stable, then any solution which starts out sufficiently close to x hat stay close in the sense that this norm remains small, and in addition the solution asymptotically approaches x hat in the limit as ten approach to infinity. So the feedback linearization of autonomous nonlinear system is the second method that we study. The general form is in this form. This method first we aim to find the linear form for the control law. We linearize the system as following, having this relation and then find the parameter that yield this linearization. there are some key conditions. One of importance is the relative degree is equal to number of the states equal in the joint. If it's less than n, it's mean zero dynamics. So we take Ax equal this form equal minus the inertia matrix cross the F equal Coriolis cross Q dot plus gravity term. The torque equal U is constant. Also this is D. The constraint of from this we have constraint and this overshot come for this method is first that the inertia term is must to be completely inversible to have solution, and there are the second is to have information for inertia matrix gravitational term and for the friction. It's require full knowledge for that. By taking this form we can make the input law as this for feedback, and then we can use pole placement designing and define state equation as this. So we can make the step R as Rd equal how many times we must derivative y for q to get the u. Number 2, designing for alpha x equal Coriolis q dot plus gravitational term, and bx that realizes the gravitational term or inertia matrix. So the developed torque become the control law, then become linear, as well as this form is called double integrator method. Then we will study the stability analysis. The complexity of nonlinear system for stability due to it can have one equilibrium and more equilibrium points, as mentioned above, limit cycle for resonant manipulators, chaos behavior. Then we introduce the Leonov method, indirect or direct method. Indirect first linearization model that depends on linearize the also it depends on an equilibrium point of nonlinear system and the linearization of the system. And then we can treat it as a technique in which stability of an equilibrium point of a nonlinear system is evaluated by examining the stability of an associated linear system. Then the steps are linearize the system and define delta xt equal xt minus z to take the variation of xt about x, the distance from the origin, yes, and then expand it by Taylor series expansion. We say that we can see delta x dot equal the linear system with the constant torque, then expand it to this form and dropping the higher order terms, then we get this form, Jacobian matrix cross delta x. This is linearized about operating point xu equal x dot the equilibrium state and constant torque. It tells us that if all of the eigenvalue of the Jacobian matrix lie on the left half of the complex plane, then the equilibrium point is asymptotically stable. As well as this form. and if you check the eigenvalue of this form to the k of this matrix, we get that it's symptotically stable if and only if the real part of the eigenvalue of the kth joint is less than 0 is the condition for this stable. The second method to investigate the stability is the direct method, direct applied to nonlinear system, and it depends on the energy function, or what's called Lyapunov function. And in this method, it will show up the region of attraction, not only the stability analysis for this system. We take this function VL that maps the region of attraction into R. It's called Lyapunov function, and have this condition for Lyapunov function definition. It's continuous derivative, and when its function of 0 is equal to 0, and number 3 is positive for greater than 0. Such way x is not equal to 0, but the equilibrium state must be 0 to simplify the analysis. So we can say that from the condition 2 and 3, the VL is positive divine continuous derivation function from the one condition. So torque is constant, and the domain of attraction is a set of all x that have VL of x is less than B. The condition for the attraction of region, domain of attraction or region of attraction, and this way. So the equilibrium point is asymptotically stable with domain of attraction if a long solution of Gx are constant torque. So that this condition we can say to symptotically stable for applying the Lyapunov function is less than or equal to 0. Number 2 is the derivative of it equal to 0 when xt equals 0 for each t. Since from this definition, the Lyapunov function must not increase along the solution of the nonlinear system, and intention it will not be the same value for each t, so it may be decreasing, and this is acceptable. So that the derivative of the Lyapunov function is the Jacobian of the function called the nonlinear function with the constant torque. From this, there is no need to solve the nonlinear system because there may be no solution for the closed form for this equation. Maybe does not exist. Some notable points that to be in mind: domain of attraction and zero dynamics. Domain of attraction, the direct method gives how big the stable region is, but the indirect method is only describe the local. Zero dynamic, if we only control output y equal the gravitational term of the state of the remaining states are the remaining states stable, so we can check this for this question. For feedback linearization, this is the form, and then we can investigate the stability. We can define the function depend on the error of the error dynamics of the system like that, so that the x double derivative, the second derivative of x state, desired x state minus kd e dot minus kb cross error since error equal x1 minus x desired x state, defining the Lyapunov function as this. That is the control law. Sorry, that's control input. That is the linearized control input, not the Lyapunov function. This is the Lyapunov function definition in this form. Then when we take the derivative of it in the function of e and the derivative of error is take this form. If the derivative constant is greater than 0, this is yell that the derivative of Lyapunov function is less than 0. For derivative of error not equal 0, this is satisfies the Lyapunov condition, so it is stable for that. For now investigate the stability for the constant solution method. First, equilibrium equal, as we mentioned, equal the constant solution. Next, linearization around constant solution give this form, and then the feedback control law equal in this form of the state. Then prove the Lyapunov stable for the matrix of this form that linearize the model. So A depends on the inverse of the inertia matrix, and C and delta H. Also B depend on the inverse of inertia matrix. مثال بسيط لسنجل اكسيس روبوتيك انفيرتد بندلم. اول حاجه هننشئ الستيت ايكويشن، بعدين نعرف المتغيرات حقتنا كالاتي، وبتضح لنا في التالي انه الستيت equilibrium have two values. Then when we apply the Lyapunov first method, the equilibrium with sign it asymptotically stable for this case because it satisfies the condition 1. For the second method, to estimate it at domain of attraction, assume R equals 0, puts the equilibrium state in this range corresponding to the arm hanging straight down. First, change variable to translate this point to the origin in this way. Then the new state equation like this form, and this in this form. Now the new equilibrium of transformed system is 0 equals 0. Is z equals 0. Finding the Lyapunov is decreases along solution of this system cancel the term of containing sin z, since the long sign at the equilibrium points because it changed the sign. So define the Lyapunov function as this, and then we check the condition that VL equals 0 and the above Lyapunov condition for the magnitude of z is less than the pi. That is the constraint to following operation which contain the equilibrium z1 is less than pi. Now VL dot in z around solutions is equal to its derivative in cross the derivation of z. Take this form. We must eliminate z sin z1 cross z2, change sign at z equals 0 by choosing by arbitrary choice of alpha and beta in this form. Since for derivation of Lyapunov function is less than or equal 0, now check condition 2 is when to be 0, when z is a function of t. Z2 is equal to 0, then the derivative of z2 equal to 0. Since that sin z1 equal to 0, that when the z1 equal k pi, but we constrain it to less than pi, so k equal 0. Then the satisfied Lyapunov and z hat equals 0 is indeed asymptotically stable. Now estimate the domain of attraction. We must find largest b greater than 0. Now define it the set of OZ that have VL is less than B and substitute the value of VL in this form. So we show that B is equal to 2 alpha. Then Z1 is less than pi as equated in constraint above. In this case, the largest possible value for Z2 is R equal this form. So is lambda. Lambda is the largest value for Z2. We can develop the first plane in Z2 and Z1 as this. Largest value in the Z2 direction is lambda and minus lambda is the minimum, and for Z1 the constraint as mentioned is a pi in two-hand direction. So the physics interpretation for the domain of attraction will be equal to alpha if arm starts out motionless, then any initial position satisfying the magnitude of Z1 when t equals 0 is less than pi will cause the arm or pendulum to accept downbeat oscillation, which settles in the stable straight down position. That's Z1 equals 0. Similarly, if the initial position is straight down and the initial angular velocity satisfy the magnitude of Z2 when t equals 0 is less than lambda, then the arm will again settle in the stable straight down equilibrium point Z1 t equals 0. The reference is this. That is the reference.